Thanks for coming. I think every once in a while when I do coding, there's kind of a library that comes along and changes how I think or build software somehow. And to me, the Ray library is like that. It's a really early stage library, but I kind of fell in love with that, and I would like to just show it to you and hopefully inspire you to maybe start experimenting with that a little bit. So if this works, where should I click now? So I'm Jan, and I like to teach computers to see. Usually doing that by teaching them how to analyze cardiac images. That's why the company I founded is called KardioMe. But also, the other part is that how can we reduce waste in production? Because we cannot avoid production, there is always something going on. If we produce electronics, yes, there will be waste. But can we at least reduce it a little bit so that we can maybe have some little impact on the environment? So there are many different things in computer vision or even machine learning. But the first thing, if you want to build something with machine learning, you want to maybe scale the thing to make something big. The talk is called Distributed Computing with Ray. And as one of the known names in software engineering, Martin Fowler says, the first rule of distributed computing is just don't do it. It is just usually a bad idea because it is a massive complexity booster. Instead of doing things on single machine, you start to now have problems with networking, latencies, and communications. Nodes go down and up, and all the nasty stuff, and you have to kind of take care of that all. But still, the world we live in is concurrent, and things are happening at the same time anyway. So there are lots of things that come into our systems, lots of things that go out of the systems, and we must have a way to process the things that come in and go out. Things that go in asynchronously, sometimes you cannot just wait for a single thing to happen, but you need to do other things. So it's like when I was coming to Serbia, I took a bus. The bus actually was probably also not a very good idea, but it took a while to get to Budapest, and then the bus was late. And so I was afraid that I will miss the second bus. So I was waiting for if the first bus will arrive on time to get the second one. Luckily, I did, and some other people from Berlin had the same problems. We kind of synchronized in Budapest and took the same bus to get to Belgrade. So there's the same thing as computer science. We call functions. The functions take sometimes longer. Sometimes some functions are faster, and sometimes we need to synchronize, and things happen all the time. Also in medicine, when you have a new patient that's coming, you cannot wait a week to make a decision if to implant a stent in the heart. You actually have to do maybe some ECG, get some data, and then you can plan a little bit, but you cannot wait more than a few hours to start to do something with the patient. Actually, the time matters a lot in emergency cardiac care and other areas. But also, not only we have to deal with a lot of data, if we want to build systems that don't fail easily, we have to build some redundancy. So if some part of the system fails, the other parts can take over them. So as I said, the machine learning, usually some tasks take shorter, some tasks take longer, and we should be able to keep up with the demand and not just burn energy paying to the AWS, to Amazon or Google Cloud for machines that we don't use. Of course, yesterday we've heard a talk about Amazon Lambda, and sometimes it is a very good option to scale massively from 0 to millions of functions in no time. But what if we need some more constraints? What if we need to build something that has little to no latency, that can respond really in real time on the spot, that we cannot afford to upload data there and back? So in Python, the whole thing about building concurrent, distributed, and parallel systems, it's been dealt with for quite a while. There are the things the use on a single machine, like threads and processes. But then you start to look into things, how you can scale beyond one machine. So you find that there are libraries like Dask, PySpark, Celery, or sometimes you're just fine with using a single thread and async when you just need to wait and the thing is not computing anything. So this is just really a tiny screenshot of the official Python page for parallel processing in Python. And this is just a part of it. There's a lot. There's a lot more. So to look into some of the alternatives, first let's see why do we need, what do we need, what are the constraints. So for example, what KardioMe was doing at some point was to build some pipeline to build anatomically accurate models of the hearts from CT or MRI images. So at the beginning, you have of the pipeline, you have a CT or MRI image, and then you go through some machine learning steps to extract the shape, the form of the heart. And then you extract the mesh from the form, and which you can then send to a 3D printer for printing with, for example, plastics or some other material. The other thing is to visualize the thing in a virtual reality if you don't want to print that, but you just want to see the heart, for example, itself. I'm not going to talk to you about the details of this. If you want, talk to me afterwards. But what I want to say is that there are different blocks, and the blocks depend on each other, and the blocks are very heterogeneous. They need different hardware. Some things work well on CPUs, some work well on GPUs, and some are just waiting for something external to happen. The other thing is that if we want to inspect things on the production line, we want to, for example, here is a cookie quality control line, where you have cookies on a belt, and the cookies come in a sequence. And you have to actually be really fast, not to influence the speed of the whole pipeline, of the whole line. And you have to want to decide if the cookies are okay visually, or if they're burned, or maybe there's some cevapcici hidden in there. And of course, you cannot discard the thing, like once your cookie comes, you wait 10 seconds, another cookie comes, and you throw it away, the other one. You have to be actually exactly sure that you're throwing away the right cookie at the right time. So there are also really these latency time constraints that you need to apply for your data pipelines. So what are the alternatives to actually make things work in Python? Probably the most known ones are PySpark. PySpark is essentially a Python interface for Spark, a set of libraries in Java that is used for data processing. It's quite complete if you want to process documents and if you want to be pretty sure that all the documents are processed in the same way. Spark is wonderful. But still, you're buying into this whole Java ecosystem, and for people that are used to Python like me, I don't like to just, if I want to process something in parallel or in faster, more reliably, I don't want to go for Java at all. That's probably the last thing I want to do. But the other options is also, if you have a Spark, you're limited to this kind of processing. You have this processing in sequences and stages. You have homogeneous tasks that process in roughly the same time something, and then you pass on to the next stage. And you have these kind of barriers of synchronization in the middle. That we don't want that, actually. Our tasks take a really heterogeneous, arbitrary time. Some takes really long, some takes really short. And we want to be able to even call new tasks from another task, because we want to be able to really spawn hundreds of millions of tasks if needed from another task. So maybe something that is more like a dynamic graph would be more useful. So for that, Celery helps a little bit, but Celery is great for connecting to Django, for example, to send emails, to send tweets, and stuff like that. But if you start using Celery for a while, it doesn't feel natural. You have these weird keywords like group change, chord map, star map, chunks. Yeah, you get used to it, of course, but if you want to call a function as a callback to another function, then there's this link, yeah, it doesn't look like Python. Let's do something nicer. Then that's where Dask was brought to my attention some years ago. Now it's a nicely mature project that can, in some cases, really nicely substitute, for example, PySpark. And it's way, way more Python-like. Also, the nice thing about Dask is that it has collections that work well with pandas data arrays, that work well with a large NumPy arrays. So if you want to work on massive images, for example, you can chunk the images into parts, into blocks, and then process each block separately by some worker. Still, Dask does not solve the latency issue because Dask itself, if you run in the distributed setting, has this global scheduler. So if you want to execute a task, the task is somehow pickled, and then it's sent to a global scheduler, which then decides which worker node is going to run the task. So that increases a little bit the latency. Also, when you send the task, that means the function plus the data, you pickle the data. And when you pickle the data, Dask is using things like normal pickle, cloud pickle, message pack, and for NumPy, to be a bit more efficient, they use something custom. So what are really the requirements that I would like to see for my systems, and hopefully it's going to be useful for other people too? I want the dynamic tasks. I really want to be able to call from one task other tasks. I don't want to use anything that's Java-like. I want to really use Python. I want to buy into the Python ecosystem of libraries for machine learning. So if I'm using TensorFlow or PyTorch, MXNet, whatever, I don't want to be specific to one single library. And I want to have really low latency too. And if one of the nodes goes down, I want to be able to recover. But of course, most of the time I develop on this machine, which, as you saw with the connector, is actually a very legacy machine. But still, I want to be able to go from one laptop to maybe a cluster to more machines without many troubles. So that's Ray. Ray is a general-purpose framework for doing distributed and parallel Python, along with a collection of nice libraries that do data processing. It's developed by people, some of the same people that developed Spark at UC Berkeley. And instead of focusing on doing this streamed, batched processing that Spark does, Ray is focused on doing really fast live predictions, live decisions. So the unique components of Ray, first of all, the API is rather simple. So you don't have any cognitive load remembering tons of things that are different from what you know. It contains stateless tasks, as Dask, for example. Or stateless task is just essentially a function that you can execute somewhere on a cluster, or even locally. But also it has actors. So what really changed my whole thing about how I think about software is also about this thing called actors. When I was preparing for using Ray, I had to go into things like that is like Akka and Erlang, and she tried to understand more of the concepts behind why Ray is using actors. To be fast, Ray actually feels like working on a local machine if you are working on a local machine, and if you're going more distributed, then it does not feel that heavy to do it. And that's thanks to bottom-up scheduling, so you first schedule the task locally, and also thanks to some shared object store that we'll see in a second. So this is really most of Ray's API that you will ever need. It's like five keywords: Ray init, Ray remote, Ray get, Ray put, Ray wait, and that's about it, really. And the rest is mostly Python, nothing really special. So tasks. How to define a task? The task, as I said, is a remote function that can be called locally or somewhere on a cluster. So by decorating any Python function, that means even Python functions that are essentially Python functions compiled with Python even, anything really that is callable with Python can be decorated with ray remote and can be made distributed function, a task. So once that the ray remote is decorating the function, what is actually happening is that the function itself, the body of the function, is pickled and it's sent to some object or function store. But we'll see that in a moment as well. The other nice thing about a task is that you can specify what are the requirements that you need. So if your task needs a GPU, a CPU, how many CPUs, GPUs, and so on. To create a task, to launch the task, to launch the execution, to schedule it for execution, all you need to do is then call the function name .remote and with the same arguments that if you would be calling the function locally. So the remote appears in the decorator plus in how we schedule, how we call the function. And that's about it. So once you call the function, once you schedule it for execution, you get immediately a future. The future is returned immediately. It's just a code for where the result will be stored somewhere in the cluster or locally. But it's non-blocking. So to get a result, you'll need to do something else. But first of all, the functions really you can run them in a list comprehension. You can then get a list of futures. The actors, we've seen some talks where some predictions depend on what happened before. So if you're working with time series data, for example, you might want to be interested in some window of 10 last samples, or you want to compute some mean over time. Or eventually building something that's called a parameter server. That's often used as an example for Ray. And why is that? Because parameter server for machine learning is something that is kind of like the book where each of the workers look into when they want to get the parameters of their models. You want to train a model in a distributed way. You want a single place where the weights, where the parameters are updated. But this is how it can be used. It's just you pass the parameter server into the functions if you want. But the actor itself does not have to be a parameter server. The actor itself can be actually anything where you need to conserve the state. For machine learning, for example, in industrial inspection, the actor abstraction works really, really well for cameras. So you have one actor per camera. You really don't want you want a single access to the camera. So you normally, in a threaded way, you would write some lock around the acquisition and all the communication with the camera. But what the actors do, they don't do any concurrent access to the object, and that's why you can even mutate the state of the actor. That's why you can update that, because all the calls that are done on the actor are queued on the actor's each mailbox, and they are executed sequentially. So you don't have to worry that 10 applications use your camera. They can, and they all can work with that safely. And there are no locks, so you avoid any deadlocks. And all the nasty stuff if you don't do the proper release in the same order as you acquire the logs, and all the things that you would have to normally think about, but these abstractions helps you to avoid that. So there are no logs for mutation, and the actors also, like the tasks, return the future immediately. So finally, to get the results, you have tasks, you have actors. To get the results back, to block and really get the output of the computation, all you need is just a ray get. And the ray get is sure that all the dependencies and all the tasks that are all required are first obtained, and once that it's done, ray get will look into what's just called an object store and get the results. So instead of doing what Some libraries do that. You define their own DSL, domain-specific language, for building of graphs. Some define that in YAML, JSON, or even TensorFlow is defining its own computational graph. This is a little bit simpler, that the computational graph is defined by running the code itself. So all the task dependencies are stored in the computational graph, and they're scheduled as soon as they are asked for. So the architecture. So this was the API, like 5 functions that you want to execute. But why is it should be any faster than other things? Why is it faster than Dask, for example? So the architecture is relatively simple, and it contains of around 5 to 6 major blocks. First of all, you have some nodes. In this example, for example, 3 nodes, and a global control state. But the thing is that if on each of the nodes you have some workers that are just Python processes that can run, that can unpickle objects and then can execute functions. But also on each of the nodes you have this local scheduler. So if on the local node you have all the data that's ready, you have all the functions that are there, and there are sufficient resources to execute the task, you don't need to go elsewhere to execute the thing. You execute it locally. So that's why it feels like working on a local machine. And if you're working on a local machine, that's what it's doing, really. If you have more nodes, then each of the nodes takes part of the tasks. But how does it know which task to take? So if a node is not able to process the task, it submits the tasks to whenever a task is scheduled for execution, it is also sent to the global control state. The global control state itself is encapsulating the whole state of the system. So all the other parts of the system are completely stateless. So if any of the other parts go down, they can be reconstructed back by the information in the global control state. And the global control state is essentially just a Redis cluster, a couple of Redis machines that synchronize the data, that shard the data if needed. So if a node goes down, and there are tasks that were not executed, this global scheduler will actually notice that there are tasks that need to be scheduled, so it sends the tasks to other nodes. So the worker and driver are Python processes that execute the tasks. They can also submit other tasks to other workers. The shared object store is what you have locally. So locally, if you want to store data, if you process, for example, if you convert an image to a number or a string or something, you store the result in a local object table. And the local object table is using Apache Arrow for serialization. Why? So Apache Arrow was designed to store objects that are used often in data science, in numerical analysis. So if you want to store a large Python NumPy array, for example, and you store it in this layout in memory that's defined by Apache Arrow. When you want another process to access the same data, so a completely different Python process that wants to access the data just needs to get a pointer to the address where the data is stored, and then just has exactly the same view on the object. So if you have 2 processes that share the same NumPy array, they just share essentially the pointer to the memory, and then you don't have to copy anything between them. So that's a nice thing. If you have processing in Python itself, you have to somehow pickle the data. You have to send it to the other process. You then have to unpickle that, and that is happening really, really fast with Ray and Apache Arrow. And it's called zero copy deserialization. So if you have a look here, for standard objects, it's maybe the same speed as normal pickle. So on the left, you see the performance of the pickle. On the right, you see performance of the Ray serializer with Arrow. But once you start using NumPy arrays or pandas data frames and things like that, then the serialization is much faster, but the deserialization is instant. So this is super useful. So you have more processes on the same machine that work on the same data with no copy. But this is, of course, not possible with mutable data. So the data is stored always in an immutable way. So this Plasma object store is a key value store. You get a key under which your data stays. If you want to modify the data, you have to push the data again, put the data to the data store, and you get another key, and then you can share the new key. The local scheduler is the other part that assigns the tasks locally if possible, if the resources are sufficient. If not, it pushes them for execution elsewhere. And the global control state, as I said, is all the metadata of all the state of the whole system. So once anything else goes down, it can recover, but except for the global control state. And the global scheduler is submitting the tasks that that no other worker was processing. So, as I said, the whole thing about doing distributed in the end is also about building stuff that can recover, that does not have too many points of failure, and this is what Ray offers. So, in real setting, in the clusters, or if you want to use spot instances on AWS, you don't usually have guarantee that the node will stay alive forever. Or you want to scale up, so add more machines, and once you add more machines, then you need to be able to reconnect the new nodes, the new machines to the cluster and compute. So if you have the node in the same state, same place, you can more easily add more nodes and distribute the load. So really, does it scale? The developers of this library use it mainly for doing research on reinforcement learning. And reinforcement learning, what it is doing, it's all about you have a system with which you interact somehow, and you get some reward. And you want to change the way how you interact, change the rules of your system based on the reward. So you want to maximize the reward over time, but sometimes it's like the reward can come not immediately, but it can come in a while. It's exactly like when we do something for ourselves, for our health. When we eat fast food, it's okay right now, but actually the reward later on, it can be, the negative reward, the penalization can be massive, but we don't know about it right now. So reinforcement learning is about learning something from these sparse rewards. And where they applied Ray was for training for example, this humanoid model to be able to stand. It's actually not a really simple problem because you have lots of different joints that need to coordinate with each other and then somehow do not fall. So that requires a lot of simulations, a lot of different initial conditions where you start with the humanoid, with the avatar. And whenever you fall down, there's a negative penalization. Whenever the longer it stays, the more it gains rewards. So at the end, it kind of learns to run, and it's fantastic, of course. But not only they were able to train this thing with Ray on like 8,192 machines, of course. I don't have the resources for that. But the other thing that is pretty interesting about it, that they were able to beat a really custom-built system that was designed exactly for this task. So Ray was able to scale up for thousands of machines and still offer a good performance. So maybe like Eugenia was mentioning that, how can we do something that is working well for local developers, for local doctors, local people, local actors in the system? But also, if needed, how can we make it faster and run in a scalable way? Okay, so to build a cluster, you need some machines, so that there's no way to go around that. But you can actually do it at home. You don't need an AWS, you don't need a Google Cloud for that. So you have some machines lying around that have reasonably good network connection between them. You can already start to experiment with that. And Ray actually offers a really nice way to, as pretty simple way to create a cluster locally. So there are commands for Ray start, where you create a head node, and then it gives you essentially the link to reuse on all other nodes to run as well. And once you do that, you create a cluster at home. And you can start using Ray. For those who want to experiment more, there are tools that do that for you automatically on normal public clouds like AWS and Google Cloud platform, including even auto-scaling. So whenever the load increases, more machines are provisioned. And when the load decreases, the machines are killed so that you don't pay for something that you don't use. But in the end, if you develop with Ray, you might think, okay, there's this weird abstraction. How do I code with Ray? It's not. It is Python. I define everything in Python, but it is being executed somewhere else. What do I do? How do I test that? How do I debug that? So testing of Ray is rather simple because all the actors themselves is just you have an input in and an input out, and that's we know how to test that. There is no race condition. There is nothing else to test really. There's one actor, and you know what should go in, what should go out. And the tasks are even simpler. It's just like regular functions, pure functions that you really have the input plus the output, and there's nothing that's changing in the middle. But also Ray offers something that's a web UI where you can peek into the central node and ask for objects in the cluster. And you can visualize what's going on, not only the functions that are executed, when they're executed in which sequence, but also what is the content of each object. And finally, sometimes you are lucky to use things like breakpoint in Python 3.7 that works, or IPDB set trace, where you, during your execution from your shell, if you put these lines into the code, it prompts you it launches the normal debugger for Python, and you can interact with the live execution, and that of course works for normal Python as well. So Ray itself is this framework where you have defined these abstractions of tasks and actors, and some shared objects. How you can share, for example, arrays between two actors, two tasks, or two processes. What Dask was doing really well was this ecosystem of collections, that you have collections that help you to scale, for example, pandas to more machines that are able to do processing in chunks of the image. Ray is not there yet, but nevertheless, it's already offering good libraries that are appearing on top of Ray. The first one is RayTune. Well, RayTune is a wonderful library for hyperparameter optimization. And what is hyperparameter optimization? So imagine you're developing a machine learning system, for example, a neural network to classify cats and dogs or something else. Now you can construct this neural network in different ways. You can add some convolutional layers, some dense layers. You can add some branches, whatever you want. Actually, the creativity is endless. But also you have to specify the parameters of the learning. How fast should it learn? How many of these layers it should have? If there is anything that should dampen the training and so on. So Ray offers something that is going to help you to find the right set of parameters for these models to use. And it's not limited to machine learning. You can, if you think about any function that you want to perform a little bit better, And you know what better means. If you can define that, it can be even the time for execution of the function. It's up to you. Then you can use this concept of hyperparameter tuning. And to do that, Ray offers two APIs. The first one is the function-based API, where all you need is to wrap the function such that it takes a callback to some thing called reporter, and the reporter is telling you how well the function is behaving. And in the body, you can do anything. But most of the time, the body itself is training. It's training some model. But the other thing is also class-based API. So if you want to do some checkpointing in the middle, you can do that. So how to specify which parameters it should learn? There is a spec for that, which is experiment config. Either you can do that in normal Python dictionary, or if you want to have some more safety and type checking, there is an experiment class that is helping you to take out all the parameters and validate them. And essentially, there are two important things. There is this thing called config, which is a definition of parameters that it should go over. How should it try which combinations? So if I want to, for example, have a look at if there is a cat in the image or not, and I want to see how many of these layers I should put, maybe this one of the parameters should be the number of layers. And Ray tune will sample all the different combinations. And there are different ways to schedule and so on and so on. And it's growing. So I really like to encourage you to have a look at that. Once you have your models trained, everything is exported to something that's called a TensorBoard format. People who use TensorFlow know probably TensorBoard. And TensorBoard is a visualization tool for TensorFlow. But you can use it for any library, not only TensorFlow. So once you do the tuning, you report your progress along the way of the training, and you can see which model is doing better than the other, and then choose the one for the application there. So that was Ray Tune. The other library that is, that's why actually Ray was built for, was for reinforcement learning. And the reinforcement learning is about training stuff that we don't really know how to train normally. Like imagine this hand is trying to rotate a cube into some position, and it will be really, really hard to write code to rotate the cube somehow without using another hand and trying to orient that. Or self-driving cars in the future, maybe. So there's reinforcement learning, and that's where Ray itself is wrapping OpenAI Gym, which is this kind of playground for reinforcement learning, so that it can use them. It can run many simulations of the world, and then train it. Other libraries for remote arrays and distributed linear algebra. If you have massive arrays and you want to compute SVDs, eigenvectors, and so on, that's there. And if you are using pandas, you might get some benefit of speeding up pandas by just importing a single line of code instead of import pandas SPD, import modin.pandas SPD. And if you're lucky, it's going to work straight away. Still, it's experimental. So, to conclude, I hope this was a little teaser of Ray. I know that there's a lot to cover about Ray, and I think that there are ways to learn a bit more about Ray. There are much better ways to learn about Ray by playing with that. And Ray has wonderful IPython notebooks on the GitHub. So if you go through like 12 notebooks, it's going to take you probably even less than this talk. You'll get much more insight. And you will be able to really start applying this distributed thing. Maybe if you want to replace all the parallel processing on your machine, to kill all the threading things, threading code, with Ray. So instead of doing all the mutexes and locks and so on, you can just do .remote and you're done. So don't forget to check out Ray. It's really just one pip install Ray away. Thank you.
Thank you, Jan. We have a few minutes for questions. If you can do a quick one, just raise your hand because Lido is currently offline. We had to hack our way into showing the presentation. So, any questions about Ray? What? Licenses. Yeah, Victor.
You mentioned Dask before as a comparison to Ray. So what is the thing that Ray does better or differently than Dask? Because it was a huge presentation and a lot of things you mentioned, but some short comparison maybe.
Mm-hmm. So Dask itself is a wonderful library, first of all. It's much more mature, so if you want to start exploring data, I would probably go with Dask right now. What Ray does better is for some applications, this local scheduling is really crucial. So if you want to really reduce the latency to minimum, if you want to really decide on the spot, for example, in the production line, I have to really, if each call is accumulating, for example, 10 millisecond latency, and I do hundreds of those calls, that's already a second, then my product is already away. But Ray itself can do one task there and back in like 1 millisecond. And that starts to be really interesting. The other thing that Ray does really well is this shared object store, local, the Plasma object store, that allows you to share the same data across different processes without any deserialization. So if I have one image, like I usually work with like 12 megapixel images, so that's a big chunk of memory. And if I would have to ship it between the processes by serialization and deserialization, that itself takes time and creates different copies of the images. So it also wastes memory for that. So Ray allows me to avoid that.
Okay, Jan, thank you very much. Round of applause.
Hey, PyCon Balkan. I finally did my talk. First time in Belgrade. I'm pretty happy to be here. The whole conference over here is fantastic. People are super nice, and I hope to come again next year or other years.